Hello everyone, we are team number 30 and our project name is Classifier in the Loop Anomaly Detection in Industrial Images. To give you an overview of what our project is, in an industrial setting there are lots of products being produced in the assembly line and it's very difficult to detect anomalies on an image, and we don't know beforehand what kind of anomalies are present in an image. To define what an anomaly is something that deviates from the normal expected behavior of an image, and since we can't use object detection image segmentation in such objectives because we don't know beforehand what kind of anomalies are present, we typically resort to an unsupervised approach. So approach generally taken in an unsupervised method is that they capture the normal distribution of particular pixel in a set of images, and from that they see if in the test setting if there are any deviations in that particular pixel. The current state of the art unsupervised approach for anomaly detection is called PADIM, which is patch distribution and image modeling. Just to give you an overview of what the current method is, they send a set of n normal images. Normal images are the ones which are considered good. They send it to a feature extractor. A feature extractor can be a ResNet 18, it can be a wide ResNet, etc. The, the choice of the feature extractor remains uh, redundant to the setting at hand, and then you have a feature extractor. The feature extractor takes in all the images and then it produces an output of the same size of the image. And what we do is we actually model the entire image on the distribution, and we see that each pixel falls under a distribution. Once this is done for the good set of images, the test set is then produced for the same feature extractor, and each pixel is calculated, and a distribution is calculated for each pixel, and then they see whether that pixel falls within the normal distribution or not. Now, under this particular assumption, the feature extractor generally is trained or it is pre-trained on ImageNet, and there is no bias toward of the feature extractor towards the set of n normal images. And our assumption is that if we could somehow make the feature extractor biased towards our set of n normal images, the accuracy and the performance might be better. So ours is a semi-supervised approach. So what we do first is we take this n set of normal images and then we do a binary classification. The binary classification is done in such a way that the class 0 will be a set of n normal images and the class 1 will be set of random ImageNet images. Nothing from the set of n normal images are used for this, and then a binary classification is done so that the binary classifier actually predicts whether an image falls into our set of n normal images or is it a random ImageNet image. So what this does is it kind of biases the feature extractor to our set of n normal images. Once this is done, the weights of the binary classifier is transferred to the feature extractor, and then the same setting and the same procedure is done. That is, we send the set of n normal images again to the feature extractor, but now the weights in the particular feature extractor is biased towards our data set, and then the same thing is done. That is, distribution is calculated for each pixel, and in the test setting we see if a particular pixel is deviating from the distribution. So when the dataset that is considered for this particular task is called the MVTech dataset, which has around 15 classes. 10 classes belong to the object classes, that is, it contains objects in the images. It can be a pill, it can be a screw, etc. And then 5 classes belong to the texture classes. They can be carpet, tile, wood, etc., where the entire image is the class itself. And we outperform PADIM on two metrics, that is, image level ROC AOC score and pixel level ROC AOC score. So the ROC AOC score is used for image level just to see if a particular image has an anomaly or not, and the pixel level ROC AOC score is used so that if a particular pixel has an anomaly or not, and whether our corresponding mask that we produce, how accurate it is with respect to the ground truth mask. And we see that in this particular table, we see that our method outperforms PADIM on all the three approaches, that is, on object class, on texture class, and on the mean of both object class and texture class. And this is how we use a plug and play approach to kind of take any unsupervised approach and have a binary classification pretext task before the unsupervised approach, and this can be used for any unsupervised anomaly detection approach, which makes it easy as a plug and play approach, and we add very little overtime in terms of compute and efficiency. So this is our project, and this can be used in various settings. Just to give the viewers a sample of how the outputs look like, uh, this is the image that you can see on the left. This is the ground truth, and this is the predicted heat map. The more red a particular heat map is, that means it's more anomalous. And then we also do, this is the predictor mask, and we draw a line around the anomalies. And so we can see here that there are multiple classes, and these are our results. So this is our approach, and thank you for taking time to view our project.